Our project focuses on developing a method to convert upper extremity IMU data to OpenSim. The motivation for our project is twofold. First, there has been little standardization of IMU measurement methods in previous experimentation. Additionally, current systems that utilize IMUs typically have a black box on their inverse kinematic algorithms, making it difficult to repeat experiments. The practical goal of this project was to develop a program that would be able to import upper extremity IMU data into OpenSim for inverse kinematic analysis. Additionally, some related questions are, how does the placement and tilt of the ground IMU affect the inverse kinematic accuracy? Additionally, of the available upper extremity models, which provides the most accurate inverse kinematics from the IMU data, and why? Our experimental methods were as follows. We placed 3 IMUs on the right arm, 1 on the hand, 1 on the forearm, and 1 on the upper arm, and then we had 1 ground IMU. There were 3 different locations that this could be placed on, either the stomach, the lower back, or the upper back. With these IMUs, we did 3 Fugl-Meyer motions to simulate stroke recovery assessment: elbow flexion, shoulder flexion, and wrist supination. For the remainder of this video, we focus on the elbow flexion motion. Additionally, we used 2 different OpenSim models, one with 7 degrees of freedom and one with 17, that also included the scapulothoracic joint. These will be referred to as Kate's model and AJ's model going forward. Lastly, we used a C++ script to process the data that we get from the IMUs and perform the inverse kinematics on this C++ script as well. Since the ground IMUs were placed in an orientation with some tilt compared to the ground, we had to use a goniometer to measure the degree of tilt and then counteract for this in the processing later on. Additionally, the initial pose from both Kate and AJ's model had to be adjusted based on the subject pose and the visual approximation. As mentioned previously, we have 3 IMUs that were placed along the arm, and we have ground IMUs that were placed around the body, on the stomach, lower back, and upper back. To ensure data consistency, though, we made sure that the motion was measured with all 3 IMUs attached. But only 1 ground IMU was used for data analysis at a given time. The same motion was used for both Kate and AJ's models. Elbow flexion was done to 90 degrees. In order to compare the different ground IMU placements, we plotted elbow flexion versus time for all 3 ground IMUs on both AJ's model and Kate's model. In both models, the lower back had the most accurate results. The elbow flexion angle was plotted both before adjusting for the tilt and after adjusting for the tilt. For Kate's model, we see that the lower back has a very similar profile, while the upper back improves. For AJ's model, we also see that the lower back and upper back both improved in getting closer to 90 degrees and thus more accurate. The stomach did not in both experiments, but we attribute this to the skin and soft tissue. Here we see the real motion shown side by side with the different inverse kinematic motions for both Kate and AJ's model. First, we show Kate's model before the initial position was corrected, and then after. Additionally, we show AJ's model, which has the scapulothoracic joint. We plotted all motions for different ground placements, with or without tilt adjustment, and with both models, and we see that the RMS error, which is the difference between the actual value and 90 degrees, was best in AJ's model, with tilt adjustment, and with the lower back instead of the upper back. We see that the tilt adjustment is not consistent between trials because you have to remeasure the angle after every experiment. Some future work that we would like to do is to try using different calibration methods from the Beauvier 2015 paper, including static, technical, and functional methods. We'd like to use mocap validation rather than just assuming 90 degrees. We would also like to use the auto tilt correction from the acceleration data of the IMUs rather than having to use a goniometer, which is less accurate. We'd also like to use a sternum strap for the chest in order to get better data, as well as better model the scapular dynamics with muscles, joint limits, and contact forces. We would like to give a special thanks to Mazen Alborno and Professor Scott Delp for their help with this project. All additional information concerning this project can be found on our Confluence page at the link below.